So welcome everybody to our 10th webinar on the Ready, Set, Roman training series. This training series is being put on by the Science Support Center, SSC, at IPAC, as well as the Science Operations Center, the SOC, at Space Telescope Science Institute. I'm Tiffany Meshcott. I'm the Community Engagement Lead for Roman at the SSC, and I'm excited to welcome you all today to an exciting series of presentations about the community products from the project infrastructure teams, or PITs. So the presentations today will be on 3 of the PITs. First, we'll have the High Latitude Imaging Survey PIT, or HLIS, which will be presented by David Weinberg, and then we'll have the Galaxy Redshift Survey GRS, which will be presented by Nikhil Padmanabhan. And finally, we have the Supernova PIT, which will be presented by Rebecca Hounsell. And just a note about logistics, if you want to ask questions during the presentation, you can post them in the chat. And if it's really pressing, I'll read it out during the presentation, but we may wait to the end to do all the questions at that time. Okay, this is the next slide. So this is our schedule of the upcoming presentations for our training series. And just a reminder, the goal of these webinars is to help you prepare for the call for proposals in cycle 1. So we've already had 9 webinars, as you see here. And all our slides and video recordings are available on our Outer Space page and on our YouTube page at Nancy Roman Sci. And you can go there to see the presentation from last week, which was about the other 2 PITs, the ARGIS and RAPID PIT. And you can also join our mailing list to stay up to date with the upcoming webinars. Okay, next slide. So what are the PITs? The PITs are the project infrastructure teams that NASA selected to assist in the development of software, simulations, and data pipelines for the science community. So the PITs are developing the infrastructure to enable the community to do science. And there are 5 PITs. There's the HLIS Cosmology, GRS, Supernova Cosmology. These first 3 are the ones we're going to hear from today. And then there's the RAPID and ARGIS PIT, which we heard from last week. Right. So before I introduce those PITs, I wanted to note that the Roman project has made available a document listing all the PIT and WFS products that will be available in cycle 1 and can be proposed against. So you can find the direct link to the PDF here at this QR code, but you can also go to the late breaking news page and see it pretty much near the top. Okay, so let's introduce the first PIT today. This is the High Latitude Imaging Survey, or HLIS Cosmology PIT. And David will get into this in more detail in a moment, but this PIT is focused on building the infrastructure to use gravitational lensing to understand the dark universe. I've listed here a summary of some of the goals from the team, and be sure to check out their webpage here on the right for more up-to-date information about their progress and about the team. Okay, this is now about the Galaxy Redshift Survey PIT, or GRS. So GRS will build simulations, modeling tools, and statistical analysis framework to put constraints on dark energy with Roman. And again, I won't get into all the goals in detail, as Nikhil will discuss this in his presentation in a moment. But be sure to check out their website for all the updates about their team and their progress. Okay, finally, we have the Supernova Cosmology PIT. This PIT will develop a comprehensive pixel to cosmology framework to use the type 1A supernova out to Z of 3 as probes of cosmic expansion and dark energy. Again, here's the goals and summary, which Rebecca will speak to later in this presentation. And go check out their webpage for all their updates on the team and their progress. Okay, so here's just an outline of the presentations you will hear today. So we'll start with a presentation on HLIS Cosmology PIT, and then from David, and then the GRS PIT from Nikhil, and then the Supernova PIT from Rebecca. And remember, you can always put questions in the chat anytime, or you can save your questions for the end, whatever you prefer. Okay, so now I will pass the floor to David, and I will stop sharing this and share the other slides. Let me do that. Share. Just one moment. Let's see. Where is it? I think I can share this whole screen here. So let me make this full screen slideshow. Okay, can everyone see that?
Looks good to me.
Okay, great. Thank you. Take it away.
All right. Thank you, Tiffany, and thanks everyone for being here. I'm David Weinberg from Ohio State, and I'm presenting on behalf of the HLS Cosmology pit. Some of my slides, particularly the last one, are adapted from a presentation at the last AAS meeting by Rachel Mandelbaum and Michael Troxel. Overall, we're a team of roughly 100 people, senior scientists, postdocs, students. It's a big team, big effort. If we go to the next slide. HLIS is the abbreviation that we at least use for the imaging component of the High Latitude Wide Area Survey. And to remind you what the parameters of the Wide Area Survey, I've included this image from the docs, which shows the sky area covered by the Wide Area Survey. So in the medium blue is the medium tier of the survey, which is 2,400 square degrees. And the imaging component of that is Y, J, and H bands. It will also be covered in GRISM spectroscopy, as Nikhil will tell you about. And for weak lensing, which is our focus, we expect the effective source density there to be something like 40 galaxies per square arc minute. There's a wide tier shown in light blue, which is 2,700 square degrees, and that will be imaged to the same depth, but in H band only. And then particularly important for our discussion of the first year data products, which I'll come to, is the deep tier, which is partly unique in science opportunities, but also used for calibrating and testing the techniques that we're using in the larger area. And it's two 9.6 square degree fields shown as those dark blue dots. And those will be imaged in 7 bands, one of which is the wide F146 filter, to about 10 times the depth of the medium tier. They'll also be observed in spectroscopy, as Nikhil will tell you. And then a subset of that will be observed to about 30 times the medium tier depth in just YJH. Next slide, please. So on the right here, you're seeing the scan pattern, which for one pass is 3 dithers, and each by roughly half a chip width. And the overall pattern of the High Latitude Imaging Survey is one pass like this, and then another pass at another roll angle several months later. So in total, 6 images on a typical point on the sky. And the SOC is going to produce prompt L2 images from the individual exposures and L3 images that combine the dithers from a single pass. And then on some later time scale, they'll provide images that combine the 2 passes, and they'll provide catalogs. And in the SOC data products, it's the drizzle algorithm that's used to combine images. And for many areas of science, that will be sufficient. And if you're interested in galaxy evolution, in searching for high redshift quasars, and looking at stars in the Milky Way, it may well be that the SOC data products are going to be the things that you go to because they're available the fastest. But if we go to the next slide, the thing that our pit is trying to do is provide to the community data products that really enable doing cosmology with weak lensing and galaxy clustering. And it's the weak lensing measurements in particular that are very demanding at the high precision that Rome will be able to achieve. So we're aiming to provide those data sets, to provide tools and codes that use those data sets to produce cosmological results. those will be things that you can apply, but also you can modify and apply in different ways from how we did it. And our team also aims to do our own cosmological analyses using these tools. So why is this hard? Well, typically the weak lensing distorts a galaxy shape by about 1%. And we're aiming to measure that 1% signal in the correlations of galaxies with a cumulative signal to noise of something like 1,000, and still to be limited by the statistics rather than by observational systematics. So that's what makes this a tall order, and two examples of how this flows down to requirements are that we have to know the size and ellipticity of the point spread function to better than a part in 1,000 in order to get unbiased weak lensing measurements. Next slide, please. So the data products and tools that we plan to provide, this is looking at kind of the final survey data products, and then I'll come back to the first year in the next slide. But one will be co-added images from these two passes in each Raman photometric band. And in contrast to the SOC combined images, these will use this IMCOM procedure that's described in this Harada et al. 2023 paper and subsequent papers that is designed to produce a uniform and well-calibrated PSF over the whole field. And that's what really, that kind of image combination is what's needed for the weak lensing. So we will also, from those images, produce galaxy catalogs that will have our fluxes in the Raman bands, fluxes in the LSST bands based on force photometry, and shape measurements that can be used for weak lensing analysis and weak lensing shear estimates based on these measurements. We'll also provide photometric redshift estimates and errors on these quantities. So that will be galaxy catalogs. From those galaxy catalogs, we will also produce cluster catalogs using one or more algorithms, although cluster catalogs are things where you may have your own preferred way of going from the galaxy catalogs to those, but we'll provide our list. And then measurements of the correlations of shear, cross correlations of shear in galaxies, and the galaxy autocorrelations themselves and cross correlations with clusters. So I'll provide all of these correlation functions and angular power spectra for samples of galaxies that are assigned to bins, and those bins are supposed to be, at least as well as we can, separated in redshift. So those are the basic measurements, basic statistical measurements we're going to make and provide. And then there's ancillary data that you need if you want to use those, those measurements for cosmology. In particular, what's the redshift distribution of the galaxies in each of those bins, and also simulations of the survey data that we use and you can use to test for biases and other effects. And we're also developing a framework of cosmological inference code that works on these measurements and produces results. We'll provide that code. So again, you can see how we're doing things, but also you can make your own changes to that. Next slide. So here I'm focusing on the first 2 years, and based on the current schedule, we expect that that one of those deep tier fields will be imaged to its full depth in 3 bands by the end of July of 2027. And then the kind of full observations of both of those deep fields will be done by February of 2028. The medium tier imaging, so over that larger area, is going to start in 2027, and you can anticipate that the SOC data products will become available quickly for that medium tier imaging. For our data products, we're going to prioritize results on the deep tier for these first 2 years. And our plan is to have an early data release that focuses on the data obtained through July 2027. So we expect that will be 3 bands of the Cosmos Deep Tier. And then a data release 1 that would be based on all of the deep tier data and through February of 28. And our goal is to provide each of these data releases within 6 months of completing the data taking. So that would be early 2028 and then late summer 2028. We may not provide all of the data products for these first data releases. And the calibrations will necessarily be preliminary. I would say, remember when I gave this presentation to our team yesterday, we have lots of people who have worked on the dark energy survey, kids, and they are very aware that usually it's about a 2-year gap between getting data and producing a weak lensing catalog. So, we are working in advance and we're going to provide the best things that we can in these early data releases, but part of the point of getting out data is for us and for you to also find the things that we need to improve. But with that, this first data release should enable cosmological analyses of weak lensing and galaxy clustering over this area. This is something like 10 times the area of the premier space-based weak lensing catalog to date, and it will have much higher data quality, much better calibration, and so forth. So although it's still a relatively small area, it's really a unique data set, and we encourage you to propose science against that. And if we go to the last slide, this is now a table of all of the data products that we anticipate producing for the full survey. And again, most of these we will be providing for those 20 square degrees in the year 1 and 2. The simulations are probably the thing that are a lot of the work, but we may not have simulations in particularly the early data release simply from absence of time. And there are a couple of backup slides that give kind of flowcharts of some of the analyses, but I think I will stop there and take any questions.
Okay, if people have questions about this presentation, you can ask it now. You can also save it to the end. Okay, we'll let people ask them in the chat and we can respond to them later on. Thank you, David. That was very, very clear and helpful. Okay, let me stop sharing my screen. Okay, and I will hand it to you, Nikhil.
Let me just make sure
As you get set up, we do have one question for you, David. Will catalogs, etc., be produced for only the stacked data or also the individual passes?
So I think that probably the answer is only the stacked data because the individual passes can there are things you can do with the SOC data products, and we don't necessarily have enough constraints for the IMCOM to really perform better. But I'm not certain of that answer. We might provide some things for each of the 2 passes, but still combining those 3 dithers.
Thanks, David. Okay, if there are any other questions, people can post them in the chat and we'll get to them at the end. All right, you can take it away, Nikhil.
Great, thank you, Tiffany, and thank you, everyone. My name is Nikhil Padmanabhan. I'm here presenting for the GRS, the Galaxy Redshift Survey PIT. And Tiffany already mentioned the sort of broad overview of our PIT, but I just wanted to sort of reiterate our goals are really to sort of enable robust measurements of all types of galaxy clustering, but in particular, the science that we're particularly driven by is to go after the large-scale clustering, to go after baryon acoustic oscillation and redshift space distortion signals using the Galaxy Redshift Survey with an aim to measuring what the expansion history and growth rate of structure in the universe is to go after dark energy. And to sort of enable all of that, our PIT sort of has tasks that range from simulating the data, analyzing and sort of understanding the observing program, building tools to sort of do systematics mitigation, and then producing high-level data products that enable all of the science. And in all of these, we hope to support the community in doing very similar science. So I wanted to spend a minute just talking a little bit about, let me see if my slide changed, talking a minute about the science enabled by the PIT data products. And there's sort of three buckets this falls into. The first are any kind of clustering measurements, whether they be small scale or large scale clustering measurements. These require more than just the Redshift catalog. They require sort of a selection on which sets of redshifts are good and can be used for clustering measurements. It requires an understanding of what the selection function is, most often characterized random points, but also as masks. Weights that sort of appropriately tell you which objects you want to be using as we go through the various pieces. And then in doing any sort of downstream cosmological analyses with the Galaxy 3D clustering, we hope to be able to sort of give you the likelihoods and the tools to sort of just directly use with standard codes. We also hope to sort of enable science with any class of sort of spectrally derived quantities like stellar masses, star formation rates, etc. So I'll talk a little bit about these. And then the final bucket is any science where you imagine you would benefit from going back down to prism images and analyzing these. And if you would require simulated prism images, one of our goals is to produce a suite of these simulated prism images with increasing degrees of realism. I put some numbers down for what the Galaxy Redshift Survey is aiming to sort of hoping to get over different redshift ranges out here, as well as sort of the rough line fluxes out there. Some of these are sort of also documented in the ROTAC report and the sort of appendices in there. So to talk about our data release, we sort of divided it into sort of four nominal data release segments. We have a pre-launch data release happening towards the end of this year, maybe a little past launch, but around launch. We've got what we're calling our DR1, which will be the early data, which going back to David's slides, High Latitude Galaxy Redshift Survey. The data sort of comes in both the medium and the deep tiers, and here we're focusing in on the deep tiers, so roughly about 20 square degrees of that data. And then DR2 and DR3 are sort of mid-mission to the final data release. So when we're about half the high latitude medium tier survey, and then the full survey out here. I should say this is a nominal plan, and many of these data product details will sort of get finalized based on the input we receive from the community, especially in forums like this one. So let me break down and sort of give you a table of the data products that we're planning to produce out here and a timeline. I'm going to go through all of these in some detail, but you can see they range from sort of catalogs to mock catalogs to simulations, and all of the tools that are used to produce all of these data. And so what I'd like to do is sort of walk you through each one of these in a little bit of detail, highlighting the ones that will be available for cycle one, and then the sort of general proposals as well, products as well. So one of our primary cycle one and immediate data products that we're working towards are these sort of prism simulations with as much realism as we can put in right now. And then as we learn more about the instrument, increasing that amount of realism that goes in. So these prism simulations include realistic catalogs to match observed spectral templates and physical properties, as well as sort of realistic stellar densities and distributions for each of the pointings. We plan to sort of release these with the latest versions of the Roman optical model for the GRISM. This is work from the SSC here, as well as spectral images that sort of track, that sort of match the data as you would expect to get from the SOC, matching the L2 data model. And our simulations are wrapped through Roman ISIM, so they include all of the detector artifacts and noise inputs that come in through Roman ISIM as well. Supplementing this, we'll have mosaic images that are sort of organized in the sky cells that we produce. These currently are just being produced directly through Roman ISIM and are matched to the spectral images that we create, as well as source catalogs from these. So currently, these are just synthetic source catalogs. We imagine potentially even running these through Roman Cal to sort of produce these out there, as well as the segmentation maps that come with these. And then the final pieces are the input catalogs that go into all of these, so Galaxy mocks that go in, including all of the SEDs that run through each one of these pieces. I should say we're aiming to sort of produce about 4 square degrees. We're sort of using these in collaboration with the SSC to test and validate the pipeline. So we're actively working with the SSC to validate the simulations and then make sure that the simulations match very closely the data that will come through. And we sort of imagine and this will be true about all of the data products that I'll talk about, but we imagine these to get improved as we get more survey data and understand what the Roman survey is actually producing as we go through the various periods. The next data product I want to focus in and will be available for cycle 1. And these will be the Galaxy mock catalogs that go into these survey, the GRISM simulations that I showed you. These are cosmological n-body simulations that have merger trees and galaxies painted on using the diff sky approach, very similar to what we've done for the open universe. Our goal here is to keep a data model very similar to the real data with photometry in all of the Roman band passes, as well as high-resolution SEDs on a light cone that sort of spans all redshifts up to about 4. The cycle 1 products will primarily include the inputs that go into the GRISM simulations, but as we go through more of the Roman data, we expect some of these catalogs to also be useful for understanding systematic effects, and these would be sort of large-scale catalogs that would span the full Roman footprint and not just the sort of deep tier data that we are using for the GRISM simulations. The third cycle 1 data product are sort of what we call the value-added Galaxy catalogs. And these are really designed as an afterburner onto the SSC catalogs and sort of add in additional columns to these catalogs out here. And we sort of have 3 different sets of types of columns we could imagine adding in out here. We're spending a lot of time thinking about sort of redshift quality metrics and find ways to sort of enhance the flags and information that comes in from the SSC catalog, adding in confidence flags, understanding what the residuals are, and signal to noise assessments. And the idea here is this would allow a user to subsample data based on the kinds of analyses they're looking for, whether they're doing precision cosmology or environmental studies and things like that. We talk about improved star galaxy typing using both the spectrum, but also things that we know from the photometry to improve and produce classification probabilities that, again, could be used to enhance the catalog. And then finally, galaxy physical properties. And this is something that I sort of highlighted in the slides that this enables. So examples of these could include star formation rates derived from the emission lines, or the full SED stellar masses and mass-to-light ratios, dust attenuation properties, etc. The exact set of columns that we would add to this, of course, depends on the data quality and availability. And so we will sort of look at the early data to understand where and when we can do these things, and then sort of transfer that information along down to the user so that you understand what the assumptions were, what the models we used to produce these quantities were, and what the requirements were on the data when such quantities exist. The next big piece will be the large-scale structure catalogs, and these, because they sort of require a significant area of sky, will largely focus in on the measurements from sort of DR2 and DR3. So these will happen not necessarily in time for cycle 1, but as quickly as we can get them out. And these here really would enable community measurements of a whole host of galaxy clustering statistics, which should be sort of directly measurable with many standard codes, and we plan to release a number of these as well. The data here will include sort of the positions and redshift of objects, the weights to include systematic effects, and match random catalogs that really capture what the selection function is. And I'll say this later as well, but we'll release all of the codes that were used to produce these data products, as well as tutorials on how these data products were produced. So it should be relatively straightforward for someone to change the exact selections and produce a new version of a large-scale structure catalog that is more tailored to the science. Although we hope that a lot of the catalogs we produce will have sort of broad scientific value beyond just the BAO measurements. We'll also produce measurements of the actual galaxy clustering and their covariances, as well as the codes that we use to sort of do all of these measurements. We'll supplement these with low resolution simulations to sort of understand what our errors look like, as well as the high resolution simulations to understand the systematics that I had sort of mentioned earlier. And with all of these, again, we're planning to sort of release example codes and tutorials with all of this. Let me just now talk very briefly about the tools that we're going to release. As I sort of mentioned, we're planning to have all of the codes that come in that generate all of these various data products. The codes for all of these will be public, and we plan to sort of release them as we make the data products themselves available, with examples and tutorials on how one can sort of use all of these pieces. All of the code currently is on GitHub, and we plan to make all of this public. Most of it is in Python, and so we sort of expect all of the standard tools that people have gotten used to using would be applicable in these cases. And as I mentioned earlier, we'll include example workflows and demonstrations on how to reproduce the digital results. So let me stop here with just the summary slide highlighting the products that are coming in from cycle 1, but there's also all of our data products. There's a backup slide that sort of shows you a little bit of what the data flow looks like, but let me stop here and take any questions. Thank you.
Thank you, Nikhil. That was great. We do have a few questions in the chat, but I think we will save them for the end, if that's all right. Oh, hang on, we do have one question for you. Will value-added galaxy catalogs for both Cosmos and XMM fields be available before the end of 2028?
So I suspect there will be some version of those value-added galaxy catalogs that come in from the early deep field data. So yes, that is our goal, at least.
Okay, thank you. If there are any other questions, we will get to them after the next presentation. Thank you, Nikhil. All right, now we have Rebecca Hounsell, who's going to tell us about the Supernova pit. Take it away.
Okay, great. Can everybody see my screen?
Yes, it looks good.
Wonderful. Yes, hello everybody. My name is Rebecca Hounsell. I'm one of the 4 co-PIs for the Roman Supernova Cosmology Project Infrastructure team. The others are Ben Rose, David Rubin, and Dan Stolnick. Just giving a quick bit of an overview, because I saw some other people did this, about what the High Latitude Time Domain Survey. This is the survey that has the fields in both the northern and southern hemispheres. There's imaging only in the northern and sorry, not only, there's imaging in both the northern and the southern fields, but prism spectroscopy only in the southern fields. And there'll be two tiers, one that's wide and one that's deep, so different exposure times for each one. This is also just trying to show how it will fit into the cycle 1 call as well. So there is this 180 days, which are primarily in the 2 years, but it's actually going to be split into this pilot visit, which is happening in year 1. Then there'll be like these 3 extended visits, and then there'll be approximately, I believe, about 6 months of the core component of the High Latitude Time Domain Survey. So I just wanted to put this here for people to bear in mind as we go through this talk. So, well, what does the Roman Supernova Cosmology Pit do? Well, we are tasked with creating this pixel to cosmology pipeline. And what does that mean? Well, we work to simulate both imaging and prism data in order to develop tools and software for us to extract high quality supernova light curves and spectra, and then provide these to the community. And so these are just some of the tasks that we do and the deliverables that we have written out here for you. We have a website. So the URL for this website is shown here, and this gives you a bit more information specifically about what we do. It lists our deliverables. So for simulated data, it tells you what we're doing here. And we also have, if you go to our website and go to the top right-hand corner, there is a link to our GitHub repository, which contains all the information regarding the tools that we are building. I believe there's some helpful Jupyter notebooks there as well, and some good documentation to really get a feel of what we're doing. Our team is quite large. There's something I think around about 60 plus or minus scientists which are on the team. And on our website as well, hopefully we'll go through, there's also a link to some of the papers that we've recently produced, in addition to some of the news reports and things like that that we've been involved with as well. So please do check out this website because it has lots of useful resources. If there's anything that you think is missing, or also if you want to get hold of the team, there's ways for you to do so through this website as well. So what is the Supernova Pit going to be producing? So we are really focused on getting photometry, so getting calibrated type 1a supernova light curves and host galaxy information, on doing prism spectroscopy, so that's type 1a supernova prism spectra and host galaxy information. We're going to create this data catalog where we have the supernova derived properties and host galaxy derived properties. And then we're providing tools for you, the community, to take these products and to do cosmology. So we go up to that point, and then you can use our tools to do your cosmological analyses. I'm going to talk later on about where each of these products are located, the timescales for each one of these, and where we expect them to be delivered to as well, so that you know where to look. So a little bit here, we have what we call this detection and photometry suite that we've kind of put together. The first of which is what we call Snapple. So a lot of our tools are named after drinks. There is a theme here. So we have the Supernova Pit Photometry Library. This is again all public, so you might find useful. And then we have tools to do with the PSF, these SEDs, the WCS, and file reading, just so that we want to ensure uniformity across all of our different components of analyses. This library now, uses the ASDIF model and extracts WCSs, and it's being spearheaded by Rob Nope over at LBNL and others at UPenn, UPIT, Baylor, and Duke as well. So please check out this QR code to find out more information about our library in case you find any of these things useful. Additionally, so let's go through the photometry package. Essentially, we have Sidecar, which is our detection algorithm. So this is designed to perform image differencing, detect transient sources, and evaluate efficiency and purity for supernova science with Roman. And so this also helps us to identify templates for the image subtraction as well. This is work that's been done by Michael Woodvasey at UPIT. And when we talk about difference imaging, what we really use for that is this thing here, which we call FROSTY, which does this fast Fourier transform differencing imaging, which is very fast. It uses GPUs. And we use this tool in order to do like fast photometry, like force photometry as well for our supernova light curves. And you can find more out about this through the URL, which is provided in the QR code here. And there's also been a paper published about it recently, which is now accepted and on the archive. Our main, like I said, one of our main purposes is to create these very high quality type 1A light curves for the community. And really our big tool for doing that is Compari, which is a scene modeling tool. And this is really being developed by people at the University of Pennsylvania, Carl Meldorf particularly. And we're doing some work to try to refine this as much as possible to take into account all the different systematic effects. So there's lots of different things that we need to include in our calculations to make sure that we're getting out the most accurate supernova 1A light curve as possible. As well as obtaining accurate photometry, we want to also get accurate prism spectroscopy. So to do this, we need to remove the host galaxies, which are these contaminating sources. And we make use of the fact that, you know, when we go back and revisit the High Latitude Time Domain Survey, things will be at different roll angles. So we've created this kind of linear modeling code in order to remove host galaxy contamination and really provide a way in order for us to extract the 1A light curves. And this is a lot of work that's being done over by people at Space Telescope, specifically Massimo Gregorio, I hope I'm saying that correctly, Russell Ryan, Ben Rose. And from that, we'll do this spectral extraction of the supernova. And so we've developed some different techniques. These are currently being worked on using Open Universe data. And we're also working with the team over at Duke, so with Arun and Michael Troxell, to create new prism simulations using the Open Universe framework as well. And we're hoping that those prism simulations will be available to the community later on this year, additionally. As I said, the main point is to provide these high quality type 1A supernova light curves and spectra so that then you can use the cosmology tools that we've built to do cosmology. And so one of the ones that I like to advertise here is the emulator work that people such as Vivian Miranda have been doing, who are also part of the HLIS team. So they've been doing that, building that really there. And we've been borrowing some of their time to help us in our cause as well, and thinking about how we can utilize these tools for our work. And so I just want to point to the work that they've been doing, and also some of the Jupyter notebooks that not Jupyter notebooks, Google Colab notebooks that they've been creating in addition for these for Kakara. So getting on to the timeline for delivery of our products. So, you know, we really want to try to provide any unique transient information, so like the light curves, as soon as we can to the community. But obviously this will take time for precision, more precise light curves. So the mass supported data release products, we're going to hopefully provide 6 weeks post the final observations of the pilot survey. And so that's what I was showing with the green points back previously, I think on the third slide. So the current mission plan puts us around about fall 2027. So we're also talking about having different data releases, probably on 6-month cadences from this, which will incorporate, you know, better calibration files and therefore creating more refined and more precise light curves and spectra as well. Here are some examples of some of the different schemas that we're planning. So if you want to check out, you know, what format will things be in, what are we thinking of including specifically in our different products, please feel free to click on the different links here. So we have the light curve schema, the spectra schema, and the characterization catalog that we have as well. So feel free to look at these and also let us know if you think that we're missing anything and something that we should be including. And here I just want to go through the data products table. So, you know, all things being nominal, we would hope to be able to produce this transient catalog, this transient table to MAST in Parquet format, you know, the 6 weeks post the pilot survey. The host galaxy table might take a little bit longer, likely in the second year. And this photometry, so the transient light curve, 6 weeks post the pilot survey, as we said previously, and spectrotopic spectroscopic time series similarly as well. We try to also give examples of previous ways in which we would think about delivering these data through these Zenodo records as shown here. These are some things that will be coming later, so after cycle 1, which are more to do with like host galaxy spectral references, host galaxy physical spectral properties, and training models and things like that. And the potential other products, not provided to mass, but just in S3 would be, the difference images cutouts if people were interested in those, and other calibration reference files that we would be using within our data as well. For cycle 1, we do have some potentially useful tools. So this is a tool that was developed by Rick Kessler and Rob Nope when we were working with the core community survey definition teams, where we simulated a bunch of different survey strategies. And through these strategies, we also simulated light curves and spectra. And we did this not just for these type 1a supernovae, but also for core collapse supernovae and other different kinds of transient events. I think there was also kilonovae and TDEs and other things that were included in there as well. So please feel free to look at these data to help to inform your cycle 1 proposals. Additionally, we've been working with MIDI over at the University of Pittsburgh on light curve links, which was a tool that I think was developed for LSST. And it provides a flexible, scalable, and user-friendly time domain simulation software with realistic effects and survey strategies. So you can make your own light curves. And MIDI has developed a demo notebook for the High Latitude Time Domain Survey, which you can access here. So you can simulate your own things as well. There was actually a talk that was given about this last week during the STRIDE meeting, which I believe was recorded. So if you'd like more information about that, please feel free to check out that STRIDE recording as well, or message anybody on our team through the email, which I believe we have posted on our website. And with that, thank you very much for your time.
Thank you so much, Rebecca. That was great. All right. We do have one question that is for you. People can please post questions in the chat and we'll get to them in order. Let's start with the one for you, Rebecca. How will the supernova and rapid pits work together? Both are providing image subtraction, creating transient catalogs. Yeah, it's a good question. I was actually going to ask something similar. Yeah, go ahead.
So with regards to image subtraction, the rapid pit is going to be the one that's going to be providing difference images more broadly for the general community. And I believe that and I do not want to misspeak, so please check with the rapid folks, but I believe that they're providing those to mass. And we'll, like I said, be having, if I go back on my slides, we'll be having those difference image cutouts, maybe in an S3 bucket somewhere, that if people were specifically interested in using, we could do that. I will note that we're using the tool that we're using for doing our difference imaging, the SSFT, is a similar one to what the Rapid team is also using. So there's some comparisons, and we've been talking to each other about the creation of these difference images as well. So there will be some comparable products, is what I'm saying in that respects. In terms of how we're going to work in a transient catalog way, we've started having some discussions with them about that and how we want to keep track of IDs for these different supernovae and make sure that we're not confusing ourselves and not creating two sets of things, but we're still working on making sure and finessing some of those cataloging discussions, if that makes sense.
Thanks, Rebecca. We have a question from someone from earlier for David. They say, thanks for the nice and clear presentation regarding the Redshift catalog. It states inclusion of LSST forced photometry for joint photo-Z. Do we expect the photo-Z will include calibration from other surveys, i.e. JWST or SPEC-Z? I suppose there is currently no plan on integrating deep tier GRISM for Redshift estimation. So for you, David.
Yes, sorry, I was somehow having trouble unmuting.
Yes.
So I will tell you my understanding, and if I get it badly wrong, then Chun Hao, who was on, can correct me. But so it's kind of modeled on what's been done in dark energy survey and will be done in LSST. So in the two deep fields, we will have 6 Raman bands plus 5 LSST bands to high depth, and in kind of color cells in that space, we will use spectroscopic data or higher, very multi-band photometric data sets to calibrate what is the redshift distribution in cells of that very fine color space. And then in the medium tier, we have 3 Raman bands plus 6 LSST bands, but not as deep. In the wide, we have only the 1 Raman band. And so what we can then say is, in those deep calibration fields, we can say what would a shallower YJH plus LSST or H plus LSST color be, and in bins of that space, we can then calibrate to the photometric redshifts derived from the deeper multiband data. So there's sort of 2 steps. There's calibrating the Z distribution in the deep fields, and that does use external data, and then transferring that to the medium and wide tiers is based on just the photometry.
Thank you, David. As we answer these questions, I'm just going to share this slide one more time as a reminder where you can access the summary of all the data products that are available. Okay, there's a question here. I think this could kind of go to any of you, because many of you mentioned that some of your data products will be Parquet. The question is, where's a good place to start learning about Parquet? Does anyone want to answer that?
I'll say, at least from our perspective, we've been using sort of the standard AstroPy tools to write out tables. So they're Parquet, but they're very much simple AstroPy tables written out as Parquet files. We're not trying to do anything too sophisticated. We'd expect, certainly as we learn more from the SOC and the SSC with these tools, we'll have better tooling. Right now, that's what we've been doing.
Okay, we do have another question. With larger data sets acquired, does Raman plan to refine BAO measurements for better statistical constraint to measure clustering and dark energy?
So I'm not quite sure when you say larger data sets acquired. We certainly will continue as we get more data to refine the BAO measurements from Raman. We're also, where there are opportunities, I'm sure we will sort of look to combinations of Raman with other spectroscopic surveys and try to understand what the sort of BAO signal is there. I'm not sure whether that answered the question. I'm happy to sort of clarify needed.
Seems like maybe that was clear. If you have follow-up questions, you can always ask. Okay, I have a few questions. We have just a few minutes. I will ask, unless other people, you can keep jumping in the chat with questions if you'd like. Okay, let's see. A question that I had for you, David. So you mentioned that one of the products you'll be producing is these catalogs of fluxes. I just wanted to ask, like, will they be calculated in multiple ways? And where can you find that kind of information?
I don't think I don't have a definite answer to that yet, and I don't think we have a definite answer to that yet. So there might be multiple versions of the fluxes for each galaxy, or if we identify here are the things that we think are best for the purposes of the clustering and lensing applications, then we may just provide one. But it's possible to provide multiple and a recommendation among them.
Okay, thank you. Okay, Rebecca, I had a question for you. So you mentioned that you will be producing these light curves and these transient table. I guess I'm curious, what do you think, I think you mentioned this, but like, what do you think will, like, what do you think you will learn or will be modified once you see real data?
So we're obviously working to create high precision light curves, which means we have to take into account lots of different systematics and different effects. You know, we can plan right now in our way of accounting for things like brighter, fatter, or non-linearities, and we build models and test the effect that they will have and how to account for them either on a pixel level or on catalog level. But there's a difference between using things from on ground to when things are flying and in orbit and having to understand that data and applying those things there. So I'm assuming we'll learn a lot and we'll have to adapt a lot and then provide the best products that we can for the community in the timeframes listed.
Okay, thank you.
And I think that's also partly where the data releases come in as well. So as you learn more of these different calibration files. And also, I think there was a question with how are we distinct as well from maybe getting a rapid light curve versus getting a supernova cosmology light curve. Those are maybe some of the different ways.
You have your hand raised, David.
Yeah, I think just adding to that, so we're in the fortunate situation that we know a lot about the detectors, and I think all the teams are building a lot of that into simulations and data products already. And an example, and perhaps the most frightening one we at least know of in terms of things we anticipate that we won't know until after launch, is if there's condensation on the detectors that will affect the effective bandpass, and maybe in a time-dependent way. So I think that's the kind of thing which we can't really know until there's data from launch, and so we can try to be prepared to be able to calibrate it and deal with it, but we don't know what that will actually be.
Okay, thank you. Ryan has a question. The PIT document says that the number of supernova PIT deliverables are exclusively for supernova 1A, such as the photometric probability of a supernova 1A and the 1D spectra. Will there also be the probability of other, or I think maybe possibility for other classes or spectra of other classes?
So when we have an object potentially identified either through rapid or through or additionally through our detection algorithms, we would run it through a level of classification and get a probability out about whether it's a 1A or not. Now, we specifically are interested in the 1As, and so therefore that's what we would publish. Would we have the information on whether it would not be a 1A or another class? Yes, that would be a byproduct almost of the classifications that we have to do. Whether that is to be made public, that is something that I think that could be discussed. But it wasn't something that we were expected to deliver, if that makes sense.
Okay, thank you. I realize we're right at the hour. I do have one final question for you, Nikhil, if we can stick on for 1 minute. I just wanted to ask about the value-added Galaxy catalogs that you will be producing. You mentioned that one of the things you're doing is assessing a quality metric of the spectra. And I know this is really hard. So how will you be doing that? Kind of it's hard to summarize, but roughly.
So I think that's an open science question that we're sort of dealing with right now. The goal really is to say, so some of the ideas we've had, we've got a lot of members of our team who are on Euclid. And so we're trying to use as much of the information that we've learned from understanding how this works in Euclid, pulling some of those in. So any of the techniques that Euclid has used, we'll use. We're also trying to ask, can we use some combination of machine learning techniques to sort of boost up the signal to noise in some of those regions where you sort of don't fully understand what the information is. But really, it's coming from a combination. My guess as of now is that the information will come from a combination of using the photometry to sort of rule out certain sets of redshifts, for instance, and then any other pieces of information that we've learned from that point. But the exact answer to that is still open.
Thank you. Okay, just before we finish up, we do have one follow-up question from Ryan. Let's see. Oh, you did say probability. Oh, I see. Thank you, Rebecca, for responding to that. Okay, Rebecca's already addressed this. Is there any other?
Sorry,
Please go ahead.
I'm not clear. Are 1D spectra for things that aren't 1A is going to be provided by the PIT, yes or no?
No.
And if not, then how do you determine what 1A is?
Right, so we will be running through classifiers for ones that have either been determined as a 1A through imaging, or if we just have, so there'll be imaging of the region as well, or if there is spectra beforehand, we'll be running classifiers on those spectra as well. But we'll only
So this is
investigate
probability of 0.5? Is it probability
Pardon?
of 0.5, 0.9? What are we doing?
Are you meaning like what level are we using to say this is a 1A or not, using a spectra that could be?
Yeah, what's the level where you're going to provide public data?
We're going to provide public data for 1A spectra and 1A light curves.
Yes, what is the probability that you need to say it's a 1A? 0.5, 0.9, something else?
I'm not sure what we're working on. We're playing with that within our characterization team right now. And we can list that down on our website for you.
All right.
All right. Thank you. We're a little bit past the hour, so I think we will say thank you to all of our speakers again for really fantastic and helpful presentations. Just a reminder to everyone that you can go to this page to see the data products, but also all of their slides will be on our outer space page soon, and you can go to our YouTube page to see to rewatch all the presentations today. So thank you, everyone, and good luck on your proposals.